Welcome! What if I told you that you could literally write a computer's brain, a CPU, the same way you'd write an email? That you could essentially print a piece of hardware from a simple text file? I know, it sounds like something straight out of science fiction, but today we're going to pull back the curtain and see exactly how it's done.
So let's start with the big question, right? How do you actually design a computer chip? I mean, how do you go from an idea in your head to a real functioning piece of silicon? Forget the billion-dollar factories for a second. How is the blueprint for a chip even made?
Okay, let's break this down. The old way, well, it was a very physical process. You're thinking soldering irons, a tangled mess of wires on breadboards, and physically swapping out tiny logic chips one by one. If you made a mistake or wanted to change something, you had to get in there and manually unwire and rewire the whole thing. But the new way, it's a completely different game. It's all about code. We just describe the hardware we want, and a machine translates our text into a physical circuit. It's way faster, it's reliable, and you can change it on the fly.
Now, the magic that makes all of this possible is a special type of language called a Hardware Description Language, or HDL. Today, we're going to be looking at one of the big ones, called VHDL. Now, this is not like Python or Java. With a normal programming language, you're giving a computer a list of tasks to do. With VHDL, you're describing what the hardware should be. You're not writing a recipe, you're drawing the blueprint for the oven itself.
So, before we can start writing the code for our hardware, we kind of need to know what we're building, right? We need to understand the blueprint. So let's break down the anatomy of a simple, classic CPU and see what all the essential pieces are.
At its heart, a simple CPU really only has a few key players. Most are based on a design called the von Neumann architecture, which is just a fancy way of saying the instructions and the data both live in the same memory. You've got the ALU, which does all the math, the control unit, which is the traffic cop, some registers for super fast storage, the memory itself, of course, and a bus, which is basically the highway that connects everything together.
First up is the Arithmetic Logic Unit, or ALU. This is the number cruncher, the real workhorse of the CPU. Anytime the processor needs to add two numbers, check if one is bigger than the other, or do any kind of logical operation, the ALU is the component that does the heavy lifting.
Next, we have the control unit. And if the ALU is the calculator, the control unit is the traffic cop. It's the conductor of the whole orchestra. It pulls instructions from memory, figures out what they mean, and then sends out a storm of tiny electrical signals telling everybody else what to do and when to do it. It tells the ALU what math to do and tells the registers where to put the answer. It's basically the brain of the brain.
And finally, for our core components, we have registers. Think of these as the CPU's own personal, super-fast scratchpad. They're tiny bits of memory located right on the CPU chip itself. So instead of having to go all the way out to the main memory, the CPU keeps the data it's working on right this second in these registers for instant access.
Okay, so we know the parts, but how do we actually describe them in a language a machine can understand? This is where VHDL comes in. We're about to see how a plain old text file literally gets turned into a network of real transistors. And this quote from a classic textbook just nails it. It's not some abstract magic. The tools we use, which are called synthesizers, perform an almost direct line-by-line translation of our code. When you write a certain command, the synthesizer knows, they want a register. When you write another, it says, okay, they need an adder. The code is the circuit diagram, plain and simple.
So, if you were to peek inside the code for that control unit we talked about, you'd see something like this, a case statement. This is the heart and soul of the whole thing. It's basically a big list of every instruction the CPU can understand. Each line of code tells the processor exactly how to react to a command, like load this value or jump to that part of the program. You are literally writing down how the CPU thinks.
This all boils down to a pretty clear workflow, a four-step journey from idea to reality. First, you describe your CPU in VHDL. Second, and this is probably the most important step, you simulate it in software to find all the bugs. Third, you synthesize it, which is the process of translating your code into a configuration file. And finally, you program that file onto a real chip and your creation comes to life.
Now let's pump the brakes for a second and talk about that second step, simulation. Because here's the deal. In the world of hardware, you don't really get a do-over. A bug in software, you push a patch. A bug in silicon, oh, that's permanent. And it is incredibly expensive to fix. This is why testing isn't just a good idea, it is everything.
So how in the world do you test a piece of hardware before it even exists? Well, you write more code. We build something called a test bench. It's a whole separate program whose only job is to put our CPU design through its paces. It pretends to be the outside world, throwing every possible input at our design and then checking to see if the output is exactly what we expect. It's a virtual stress test for our virtual CPU.
And this is why all that testing is so non-negotiable. Check out these industry numbers. Nearly half of all new chip designs, they fail on the first physical prototype. Even after they fix those bugs and make a second version, 20% still fail. Getting this right is hard, and the stakes are absolutely massive.
Because the cost of failure isn't just the $500,000 it costs to make a new mask, which is like the stencil for the chip. No, it's the lost revenue. A single bug can delay a product launch by months, and for a big company, that can mean a potential hit of $500 million in opportunity cost. You just can't afford to be late.
So where are all these show-stopping bugs even coming from? Well, get this. A whopping 43% of them are just plain old logical or functional flaws. These aren't weird, deep physics problems. They're just mistakes in the design. They're bugs in the code that, you guessed it, probably could have been caught with a better simulation before the design ever went to the factory.
All right, so we've designed our components, we've written them up in VHDL, and we've tested them relentlessly in simulation. Now, for the best part, the payoff, bringing our design to life on a real physical chip.
And the stage for this performance is a special kind of chip called an FPGA, or a Field Programmable Gate Array. The absolute best way to think about it is like a massive board of digital Legos. It's a sea of unconnected logic gates and wires. When you load your VHDL file onto it, you are literally telling the chip how to wire all those little Lego bricks together to become your specific design. In our case, a CPU. And the best part? If you don't like it, you can just wipe it and reconfigure it into something else.
And here's a peek at what that looks like in the real world, from a hobbyist project that did this exact thing. You can see the entire CPU core only takes up 122 little logic cells and 71 registers. That's just a tiny fraction of the resources on even a low-cost FPGA. It's an incredibly efficient way to build.
Before we make that final leap to the physical chip, we look at something like this one last time. This is a simulation waveform. You can think of it like the CPU's heartbeat on an EKG monitor. Every line is a different signal inside our design, and we can see exactly how it changes with every single tick of the clock. This is our final visual confirmation that the logic is solid.
And you know, the most amazing part of this whole story is how accessible this technology has become. This isn't just for billion-dollar tech giants anymore. We've seen a team of students build a fully working 8-bit CPU for their senior project. We've seen a hobbyist fit a similar design onto a tiny FPGA board that costs less than a new video game. The power to literally invent your own hardware is out there for everyone.
So there you have it. That's the incredible journey from a text file to a working piece of silicon. We've seen how simple lines of code can define a complex machine, and how that machine can be brought to life on a real chip that you can hold in your hand. Which really just leaves one final question for you to think about. If you can write your own hardware, what will you build?